Alright, so now that we've dealt with the binary acids and a little bit of terminology, we can start looking at more complex cases, which are, as you can probably remember from General 1, the so-called oxoacids, or more properly, the polyatomic ion-derived acids. There's no general good term for that, so we use oxoacids, acids that have lots of oxos around, oxygens. So here's how the naming setup goes. We go from a suffix of ate to a suffix of ic, acid. So the carbonate ion, if we replace all the charges, that's how we make an oxoacid, is to replace all of its anionic charges with hydrogens, or balance them out with H pluses, that is. So for every negative charge in the polyatomic ion, there's one H in the acid. So carbonate becomes carbonic acid. Nitrate, following the same trend, becomes nitric acid. Phosphate, phosphoric acid, a little bit different. Sulfate, sulfuric acid. Perchlorate, perchloric acid. The per on that bottom one is the curiosity that chlorine actually exists in multiple different polyatomic ions. And the most common one, which is how the ate suffixes came about, doesn't happen to be the one with the most oxygens. So they had to add one to it, so it becomes hyper oxygenated, more oxygen, so perchlorate. I kept it here because structurally it's going to help us understand why it's the strong acid that it is. If we start looking at the dissociation, this looks a lot like what we saw for the binary acids, and that is a strong acid with water will dissociate to a hydronium ion and a polyatomic ion in this case. And we're still going to be looking at the very same problem as we were before, and that is, can we explain why a strong acid produces a conjugate base that's very weak? So we're going to be looking at that conjugate base and trying to see if there's a reason why it would be unreactive. Why would it be stabilized? That's a big question. Why would it be stabilized? That's what it means to be non-basic for a conjugate base. Once again, in this case even more importantly, we cannot work with formulas. Formulas are uninformative until you are used to what they actually stand for. Think about it as an abbreviation. You're using an abbreviation, you better know what it means. If you come up to somebody on the street and say FOAD to them, you better know what you just said, because otherwise you're not going to understand why you get your ass kicked. Okay, so we need to draw this out in a Lewis structure to understand what's actually happening. Now, with the period 3 elements, they're actually capable of expanded octet rule things. They can go beyond the typical 4 covalent bonds up to the number of valence electrons in their outer shell in the atomic state. So chlorine in the atomic state has 7 valence electrons. By using d subshells, d orbitals, it can actually unpair all 7 of them. So it can form up to 7 covalent bonds. Well, that's what you see here. The actual Lewis structure for the perchlorate anion, the conjugate base from perchloric acid, has 7 covalent bonds to it. There's 2 to each of the oxygens, except the one that used to have the hydrogen on it. It only has 1. Well, why would that be stable? We're looking at something where the charge is on an oxygen. Well, if that were just OH, then it's a base. So how can this be a very, very weak base when changing that chlorine out for something else would still be a strong base? So there's got to be something going on there that's making that oxygen better able to handle having that negative charge on it than it would be otherwise. So if you think about it, you can draw that Lewis structure one of 4 different ways. And that is, you could draw it with the negative charge attached to any one of those 4 oxygens and multiple bonds, double bonds to all of the other oxygens. This is just formula to Lewis structure with a little bit of understanding that we're in period 3, so we can go beyond 4 bonds. Realistically, though, these are not just hypothetical ways of drawing it. These are actually what are called resonance structures, and they exist in that electrons can move from a charged atom, something that has an extra pair of electrons, if there is an adjacent multiple bond. So in this case, the atom next to the oxygen with a negative charge has multiple bonds to all the other oxygens, the chlorine. So here's that electron flow thing again, which you will come to see and love once you get to organic chemistry, where it actually explains pretty much everything. And that is, they're interconvertible if you just follow the electrons around. That you can actually see going from the top structure to the top left one to the top right one, the electrons from the negatively charged are starting this off, and then because that's coming into the chlorine has to let go of one of its multiple bonds, but that ends up with the exact same arrangement, just the negative charge on a different oxygen, and so on, all the way around. They actually can go over all of the negative charge can actually be distributed over all 4 of those atoms. So it's spreading it out. That's what resonance is all about. That's why it's so important. It's spreading out the hit so that you don't have so much trouble by having it be on one spot. If it's in one spot, it's more likely to want to go do a reactant. So resonance in its simplest form can be thought of as a very well-designed game of keep away with the electrons. So if something comes running at the atom with a negative charge on it here, well, they just throw the ball to the next kid and you're running at nobody. And so on and so on and so on. We can actually draw something. What I have on the left here is what's called a resonance hybrid. And it's not really a good structure in that it doesn't follow the rules of valence. But it's to give you an idea that, okay, those 4 resonance structures separately might might be a snapshot, but in reality, it's kind of a blur going between all of them. So if I just left the exposure open a little longer on the camera, I'd get a blurred view of the electrons. It would look a lot like what we draw as a resonance hybrid. And that is, there's a little bit of charge on every one of those oxygens. Statistically, assuming that's the only spot the negative charge can reside in is on one of the O's, then each of them is taking up basically about 25% statistically of that negative charge. So if you go running as a hydronium ion towards the collision that would be a reaction with one of those oxygens, well, only 1 out of 4 times that you hit the same oxygen is it going to actually have a charge on it. And that's ignoring the fact that there's transition going on between them all the time. So realistically, this is an enormously stabilizing force, and in fact makes this almost the worst base imaginable, because there's so much distribution of that charge that you just are never going to get that conjugate base to act as a base. It's never going to use those electrons for anything other than playing keep away with. So, you know, in very blunt terms, you can't get it to do anything because it's too busy playing with itself. Parallel case here, we're looking at sulfuric acid. So again, what I said before is that we're only dealing with 1 hydrogen removal at a time. When there is more than one hydrogen on the polyatomic ion, the other one is not nearly as favorable, so we don't have to consider it on the same time scale. So we can ignore it as dissociation. What we can't do, however, is ignore the fact that in this case, it's taken up a bond. Look at what happened. Chlorine case had 3 oxygens with multiple bonds. Guess what? The sulfur doesn't. One of those oxygens is busy. It can't form 2 bonds to the sulfur. It has to hang on to the other hydrogen. So we have 1 less double bonded one. And again, you can look back at this as saying, okay, this is the number of covalent bonds in the element if you unpaired all the electrons. Sulfur is in group 6. It could have 6 unpaired electrons, so that means it's going to max out at 6 covalent bonds. That's a little bit of a simplification, but it's one that does happen to work very well. So in this case, I don't have that 7th bond possible that the chlorine had, because I don't have a 7th electron in the atomic state. So what I have then is less places to spread the charge out. Look what happens. Now I only have 3 atoms, 3 oxygens that can be, at any given point, the negative charged one. The 4th one doesn't get to play. You either have to have the charge or have a multiple bond, or you get to sit out. And that's what's happening to the oxygen that's attached to the hydrogen. It is sitting on the sidelines. It doesn't get to play with the other children. So now the charge is spread out only over 3 atoms. So over 3 oxygens. So statistically, that means that each of those oxygens is taking about 1/3 of a negative charge, as opposed to 1/4 or 25% of one in the perchlorate ion. If we take that a step further to phosphoric, well, now 2 of those oxygens are tied up because originally there were 3, and we're only going to talk about losing 1 of the H's. So only 1 of those 4 oxygens in phosphoric acid is actually multiply bonded, which means we're only able to stabilize that negative charge on the conjugate base over 2 atoms, the 2 oxygens. We can't use the other 2 because they have a second bond to a hydrogen. They're not able to form a second bond to the phosphorus and participate in the resonance game. So as we go to less and less places to move the charge, we go to more and more activity for this. Now we're still in strong acid land, but we're getting sort of to the borderline. Phosphoric acid is still a strong acid, but it's basically like right at the border of strong acid to into the weak acid realm, because look what's happened. We've gone from having 4 spots to put the negative charge to now only having 2. So what we end up with is a competition here, and pretty soon we're going to end up losing. And that is that we're going to end up losing the stabilization game and be back into a case where something's actually going to react, i.e. behave as a base. The conjugate base isn't stable, and that means it's actually basic, going to act as a base and be reactive. The weird one here, and I'm going to keep it completely separate from the others, is nitric acid. Nitric acid, HNO3, its conjugate base, the nitrate anion, is the only case that we deal with that actually has resonance going on before we lose the hydrogen. And this has to do with the fact that period 2 elements, unlike the ones we just dealt with, the period 3 oxoacids, cannot form more than 4 bonds, ever, ever. Okay, that is as close to blasphemy as you will ever get, is drawing a 5th bond to a period 2 element. The point is, bonds happen because of orbitals, so you cannot form a 5th bond because you have no 5th orbital in period 2. You have an S and you have 3p, total of 4. 4 bonds, no exceptions, no way past it, no way above it, except to be in a different period of the table. You're not there yet. The 3 period of the table has 3 d orbitals. You don't use them until you get to 4s in filling up the atomic state, but they're still there and they're empty, so that when you need them for phosphorus, sulfur, and chlorine, you can use them. You don't get that for nitrogen and carbon. The 2 polyatomic ions that form acids in period 2 cannot go beyond 4 bonds ever. So as a result, in this case, the nitrogen has a positive charge on it all the time. Always. So there's always a positive charge on it. There's no way away from it. There's no way to neutralize that reasonably in any case we can come up with for this structure. And so as a result, this is a very strong acid because you're trying to get something to let go of a hydrogen. Well, that nitrogen has a lot of extra pull inductively because it's already short of an electron. It's already a cation and it's stuck there. So it can't pull them in to form a bond, but it can still pull on them because it's feeling, put out and poor. So it pulls on its rich friends it happens to be attached to. Even if it doesn't get the bond to them, it inductively pulls, which weakens the bond to the hydrogen in the acid. So as a result, we end up with a stronger acid. So same picture as before, we start drawing resonance structures. Well, we already had 1 oxygen that was negative. Once we lose the hydrogen, we have 2 of them. And that resonance can go on all the way around so that we end up with the negative charges spread out on 2 of the 3 oxygens around the nitrogen. Generally, you'd say, all right, well, that's not so bad, except for the fact that along with that negative charge, you have a positive charge right in the middle of it the whole time. We didn't have that in the period 3 elements because they could go past the 4 bond 8 electron rule having d orbitals. Since nitrogen can't do that, it is actually negatively charged, so it's a lot more happy having a little extra negativity flowing through it because it helps to offset that positive charge that it has all the time. So the fact that you have an extra negative charge here is actually still stabilizing because of the nitrogen having an extra positive charge. So while at first glance ignoring that plus, this wouldn't seem to be all that great, because you actually have the cation right in the middle of the whole time, it's very beneficial to helping stabilize the anions that are around it. So this is an extremely weak base, meaning nitric acid is a very strong acid. That's the exception, not the rule, for period 2 elements. We start looking at carbonic acid. Well, that's not really all that strong. If it was, the first time you had a Coke, it would have eaten through the front of your throat, and that would have been the end of you. This is carbonated water is its better name. You're not drinking it in its concentrated form, but the point is it's not that bad. It's not that strong, because once we lose one hydrogen off of the carbonate, we end up with an anion that only has two oxygens to work with. There's only one double bonded oxygen in the structure when you first begin it. So that's all you're going to have in terms of resonance to help stabilize it. So you have a negative charge splitting out over two atoms, and that's really all you have. But in this case, because you don't have any real electronic help, then you got something that's still reasonably good as a base. Not great, but it's reasonably good. This is a fairly weak acid, which means that this structure is fairly basic. The conjugate base is actually capable of being a base, reaction-wise. But this is a case where I want to talk a little bit about that second deprotonation, because it's an easier one to draw than some of the others. And that is what happens if you take the bicarbonate ion, the hydrogen carbonate ion, as an acid and remove that second hydrogen. Well, look at what occurs here. And this is why that second one and the third one for triprotic acids is so much less favorable. It is much, much more of a problem, because now you have two negative charges, like you had for the nitrate ion, but there is no cation in the middle. So you're trying to offset that same amount of charge without that cation in the middle to help offset it in terms of number. So as a result, you've got a much larger concentration of negative charge on all of these ions, on all of the atoms around the carbon. And so you have a 2/3 probability of having a negative charge on any one oxygen. At that point, the odds are in your favor. You know, this is not like Vegas where you don't bet against it, but this is, 2 out of 3. Okay, so you're going to have something that acts reasonably strongly as a base. So contextually, what does that actually mean? Well, compare it with the anion from the step before, the one dissociation. You had one charge over two atoms, two oxygens, 3 atoms total, including the center one. So for each oxygen, you've got roughly a 50% chance of finding a negative charge there. Well, now you're looking at 2 negative charges spread out over 3 oxygens. Now suddenly you're looking at 66% chance of any one given oxygen having a negative charge on it at any one given instant. So you're going more negative on every oxygen. Despite the fact you brought another atom into resonance, you brought another charge with it, which isn't paid for by the resonance. So you've got something that can't stabilize things as well as the case before it. Okay, so what is the practical upshot of that? Carbonic acid, its dissociation is an equilibrium. It's a relatively unfavorable one. Its Ka is 4.2 times 10 to the minus 7. Okay, so good rule of thumb. It doesn't always hold, but it's a good way to look at it to start with. The second dissociation, the second deprotonation, the second proton donation is usually about 10,000 times less favorable. And that's the case here. The second one, the equilibrium constant, is 4.8 times 10 to the minus 11, so almost exactly 10,000 times less favorable. So when we go and look at them, the strong ones that I put up, and I said the second and the third one don't matter, this is what I mean. It means that, think about it as a percentage, think about it as a grade, okay? 100 points in the first one, 100th of a point in the second one. Do you care? No, you don't. We do care, but in quantitative terms, they're not on the same time scale, they're not on the same favorability scale, and they're not even close. This one and a couple of others happen to be about 10,000-fold apart. Some of them are much further apart than that. That's a little bit more complicated, but the idea is that they're never going to be best friends. They're never occurring at the same rate, not even close. So we don't have to compare them as being, competing with each other, so to speak. Now we've got to look at different polyatomic ions really quickly, and that is, look at something like sulfur, where you have an SO4 ion. The SO4 2- polyatomic ion is the sulfate, so sulfuric acid. That exists in another polyatomic ion that has one less oxygen, called sulfite. So the acid that comes from that is sulfurous, O-U-S, instead of sulfuric, I-C. The dissociation looks very similar, but when you get to the conjugate base, again, if you're just drawing it out based on formulas, okay, it's got one less oxygen. That doesn't necessarily give you the information you'd like to have, but if we go and look at the Lewis structures for them, you can see it without drawing the resonance structures that, okay, the sulfate ion with the hydrogen still attached has 3 oxygens that are going to participate in resonance. The sulfite one only has 2. So you've got a lot less stabilization of that charge. A lot less stabilization means more reactive as a base. So this is a weaker acid and a stronger conjugate base as a result. Okay, so what can we use as sort of a unifying principle for the acid strength issue? It's not really easy to compare things like sulfuric acid and hydroiodic acid. They don't exist under the same circumstances. They don't exist under the same concentrations in water, etc., etc. But there is a bit of a unifying theme here. When we talk about the polyatomic ions stabilizing things by resonance, what we're actually saying is that they're spreading out a charge over a larger volume. Now, it's not typically how it's spoken, but it really is what's happening. That negative charge is actually being spread out over a larger volume of space. Well, that sounds awfully familiar because that's exactly what we said about the polarizability term for the binary acids, that the negative charge for the iodide ion is spread out over a larger volume because of the larger number of shells, so that you're actually working on, in that case, the 5 shell instead of, for the fluoride, the 2 shell. Well, resonance, if you took it down less and less, you'd end up with something very similar. You'd be taking down the amount of volume that charge is spread out over, and so you'd see something that is less and less stable and therefore more and more reactive as the conjugate base. So the trend sort of works in both ways. We don't typically use the word size when it comes to resonance because it's just about how many atoms that it's spread out over, but conceptually it is the same. If you looked at it as a volume problem, well, the volume of the negative charge spreading out over a sulfate anion with the hydrogen still attached, the hydrosulfate anion, is going to be a much larger volume than the corresponding sulfite ion from the previous one. Because you have more oxygen to spread it over, they take up space, therefore you get to move the charge over a wider volume, therefore size does matter. It is actually critical. So with that, you understand the acids and their conjugate-based stabilizations. So now you're in good shape fundamentally to understand the calculations that we're going to spend most of our time on.